So hello everyone. We are Group 13. We are very glad to have the opportunity to present here. So the title of today's presentation is called Black Box Speech Watermark Detection as an Out of Distribution Clip Level Sequence Classification Problem. This research synthesizes our two core distributions to the field of speech watermark detection, the WOX watermark large-scale benchmark, and another one is a robust detection framework. So the motivation for this research stems from the rapid advancement of generative speech, such as text-to-speech, we call it TTS in the speech area, which can now synthesize audio with extreme similarity to real human voices. Many labs such as Q1 and also COSI Wise, they did many good works on this. But however, the realism introduces many risks, including impersonation, voice cloning, disinformation propagation, bypassing voice-based authentication, and the copyright misuse of AI-generated content. So to mitigate these risks, audio watermark decision is critical, yet real-world deployment faces these challenges, such as black box constraints, compound distribution shift, and the lack of a unified benchmark. In the related work, a review of related work highlights the limitations of current research. Existing watermarking methods such as AudioSeal and WaveMark are predominantly white box or highly coupled systems, rendering them inapplicable in black box scenarios. While black box statistical detectors like WMD exist, they do not systematically account for out of distribution generalization, resulting in a substantial cross-domain performance drop. Regarding evaluation benchmarks, such as the audio benchmark and also the raw bench, primarily focus on robustness and the perceptual quality rather than systematic detector level comparison. And they fail to provide a generalized detection baseline. So to bridge these two major gaps, we propose the Vox watermark benchmark, which covers diverse watermarking methods and shapes. And we developed the XAWMD detection framework, which is specifically designed for strong generalization capabilities. Well, as for the research question, having identified the research gaps, we formulate our core scientific question. Without any prior access to the embedding process, can a detector trained on seen watermarking methods and acoustic domains reliably transfer to unseen domains and unobserved and embedded algorithms? More specifically, we aim to investigate under all the conditions is the determining of a detector's robustness, the choice of the pre-trained backbone, or the methodology used for temporal evidence aggregation. So to answer this, we conducted a systematic empirical analysis combining four backbone networks with four temporal head designs, evaluating across two unseen OOD test domains. And for the NLP task framing, to systematically address the problem, we strictly formulate black box speech watermark detection as a binary sequence classification task. The model input is a normalized 3-second 16 kHz speech clip, and the output is the probability score indicating the presence of a watermark. This task strictly requires the capacity for pre-trained representation transfer, temporal context modeling, and cross-domain generalization. Our focus is evaluating robustness under composite distribution shifts without any test time fine-tuning. And here is our dataset design. We introduced the dataset design for the Vox watermark benchmark here. The dataset is massive. Clean speech is aggregated from multiple corpora covering English, Mandarin, and numerous other languages. The watermarking methods include both traditional schemes and neural network-based approaches. We strictly maintain the class balance across all splits to ensure all unbiased evaluation. Specifically, the training and validation sets were constructed using 6 scene watermarking schemes. Conversely, test 1, which is evaluating linguistic shift, and test 2, which is evaluating acoustic, accent, and recording condition shift, exclusively utilized unseen watermarking algorithms, such as echo hiding, patchwork, and also waymark, thereby establishing a OD test environment. So regarding to the perturbation protocol, to comprehensively simulate real-world deployment challenges, we designed the 3 tiers of perturbations. One is no box, another one is black box, the last one is white box. For the no box one, we simulate common post-processing and transmission effects, including time stretching, Gaussian, background, and so on, such as in codec compression. For the black box one, we assume the detector acts as a curable oracle, testing whether attackers can flip decisions without access to internal parameters or gradients. And for the white one, we represent the strongest threat model, where the adversary processes full knowledge of the detector and attempts watermark removal or forgery while maintaining perspectual constraints. So the table here, we list the no box of the perturbation specifically. And here we want to talk about our baseline model for the benchmark. We first propose audio watermark, audio WMD as illustrated. It employs a 2-stage statistical meta detection architecture. Initially, the raw input audio undergoes stochastic transformations, and mouth spectrograms are then extracted and passed through a CNN-based detector to obtain a set of confidence scores. In the decision fusion stage, the model computes a 5-dimension statistical feature vector from these scores, including mean standard deviation, max mean difference, and the decision flip rate, and outputs the final prediction via a logistic regression meta classifier. And to achieve the superior representation transfer in all these scenarios, we proposed the advanced XAWMD architecture here. Unlike the audio WMD, which relies on spectrograms, XAWMD operates directly on normalized raw waveforms. It utilizes a frozen XLSR pre-trained speech encoder to extract the frame-level representations. Subsequently, the features are processed by a trainable temporal head comprising continuous convolutional 1D blocks, a BILSTM for modeling long-range dependencies, and an attention pooling layer. This outputs the final clip-level binary watermark decision. And here is a brief conclusion of our architecture we want to compare here. We provide a direct comparison of the design philosophies of the 3 detectors evaluated in our experiments. The reference baseline WMD originates from vision-style detection, relying on the spectrograms and convolutional backbone to output a direct score from a single query. And audio WMD serving as the benchmark baselines, introducing stability-aware modeling by aggregating multi-query statistics using a CNN and logistic regression. Our proposed model, XAWMD here, centers on learning transferable temporal representations. It entirely discards spectrograms in favor of raw waveforms, combining a frozen XLSR with a deep temporal network for decision making here. And here is our results table. In the systematic baseline comparison, XAWMD demonstrated an overwhelming advantage. As shown in the table, XAWMD, denoted as M6 here, achieved the best AUC and F1 performance across the validation set, test 1 and test 2. While all models experienced performance uh, degradation under all the conditions compared to in-domain metrics. Test 2 proved significantly more challenging than Test 1 due to its complex corpus conditions. Despite this, XAWMD remained the most stable model across domain shifts. Next, we detailed the model's robustness under compound perturbations. The data indicates that transitioning from clean speech to no box perturbation results in a significant performance drop, confirming that the common signal processing operations generally challenge the generalization. Under the white box attacks, the model maintains moderate robustness. However, the critical vulnerability lies in the black box attacks, specifically the query-based spectral domain (HSGA) attack, where the true positive rate plummet, indicating that current detection mechanisms are easily bypassed by strong spectral adversarial manipulations. Here we conducted a unified ablation study to validate the effectiveness of each component, beginning with the pre-trained backbone network. Experimental results show that XLSR is the best overall performance, outperforming Whisper and WaveLM, owing to its exceptional cross-lingual generalized speech representation capabilities. Feature extracted by Whisper and WaveLM exhibited significantly poor cross-domain transfer. This confirms that the choice of the backbone has a clear direct impact on foundational feature extraction for black box watermark detectors. Well, the backbone is crucial. It is not the sole determinant of the robustness. In this ablation targeting BILSTM capacity, we demonstrate that deep modeling of temporal structures is more critical than merely employing a stronger encoder. We observed that increasing the depth of the BILSTM stability improves joint cross-domain transfer. Specifically, when scaling to 4 layers, test 2 AUC surged from 0.665 to 0.759. Deeper temporal modeling enables the network to capture longer range, more discriminative watermark patterns from perturbed waveforms. We also want to talk about the failure analysis and also the limitations here. Despite the significant improves, the model has structural limitations. We believe here the failure analysis highlights two primary issues. First, the model struggles under a strong spectral domain, black box attacks, where DPR drops to single digits, indicating that spectral adversarial perturbations significantly corrupt or bypass the temporal modeling logic. Second, under the compound ODD conditions in the test 2, which combined acoustic shifts and noise, the model's recall drops to 0.24, demonstrating that this scenario exists the generalization capacity of the current architecture. Additionally, relying on a fixed decision threshold is suboptimal under OD shifts. To address these limitations, our future research will focus on incorporating adversarial training targeted at spectral domain attacks and developing adaptive thresholding strategies for all these scenarios. So here to give a brief conclusion here, the research sees systematically frames black box speech watermark detection as a clip level sequence classification problem operating under realistic distribution shifts. Our proposed large scale Vox watermark benchmark establish a standardized evaluation platform for testing robustness against unseen watermarking methods, languages, and acoustic domains. Through these thematic comparative experiments, we validated the XAWMD framework, demonstrating that combining pre-trained speech representations with temporal evidence aggregation achieves stronger OOD generalization than existing baseline. Our central conclusion is that temporal evidence aggregation is a more decisive factor for cross-domain robustness than backbone substitution alone. Nevertheless, performance degradation remains evident under strong perturbations and black box attacks, defining the trajectory for future technical advancements. Yep, this is basically all of our presentation here, and thanks for your listening.